Okay, so now I just want to emphasize the fact that some people think that this condition without the R being the witness of entanglement, so without it, will be a good condition. But in reality, that's a bad condition. You must know why. So basically, intuitively, just that, well, you can pause and think, but I'm gonna give the answer intuitively just to that's the fact that because you only have like one basis, like that's all we said already. Like when you have dot entanglement, like the entanglement witness, you have all the correlations, the quantum correlation that are destroyed instinctively. You can only check about the classical ones because you only check like it's 0 or 1, but you cannot check like because in quantum there is a basis 0 1 or the basis plus or minus or other basis that we just proved in the last video that even if it's not orthogonal stuff, like no matter the stuff of purification, like the other type of purification can represent something which is um, quantum correlation that cannot appear classically, and so you can think, well, okay, then what I have with this is alright because like when I measure it, like all is okay. But in reality, it's not because all the quantum correlation disappeared because but you did not see it because you were in the wrong basis about it. So the best example to understand it is EPR cubes in like C plus um, about A and R, which is equal to 0 0 plus 1 1 divided by square root of 2. And so if you check only the qubit, the local qubit A or mixed state, it's just a perfect matrix, just like rho A just equal to 1 over 2, 0 0, because like it's less or more the trace, you trace out R, and so you just want to 1/2 0 plus 1 square 1 because you take the density matrix stuff. You just have this mixed state. So yeah, and so imagine now like you just use a canal like an encoder and decoder that measures just in the qubit base in the qubit that measures the qubit in the base 0 1. Check the results, and then after recreate the qubits from these results. So it's really a weird one, it's just decoding and doing encoding, just measuring and checking about it, recreating a qubit, and so you just have one chance about over 2 to have 0, and one chance 1 over 2 chance to have 1. So if you calculate like the distance, from this stuff, you just like rho A minus D minus decoding and counting epsilon rho A, and so that's just the same, we just saw like in both cases, it just whatever our local stuff here will be like 1 over 2 of 0 0 plus 1 over 2 of 1 1. So basically here it's like 1 over 2 of 0 0 plus 1 minus 1 over 2 of 1 1. And so that's just equal to 0. And the problem is like if you change the basis about it, and we check what it is about, so this time we take AR with like plus 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 minus minus over square root of 2, which is literally the same representation as 0 plus 1 over like 0 0 plus 1 1 over square root of 2, can represent it like this too. And so if we measure our qubit this basis plus minus, he normally should be able to directly know if it's plus or minus. but because our canal will measure our qubit, like we measure if the qubit is we measure if the qubit is in 0 and 1, and so it will directly destroy the phase, and so the and so you'll just have like your AR that will be like 1 over 2 of 0, 0, 0 plus 1 over 2 of 1, 1, 1, 1, because we measure 0 or 1, and when you measure about something which is in entanglement stuff, then it will not work. It will not work, and so it will just destroy the phase, and so you just destroy it, and you just have destroyed the fact if we know or not if the state is into the bias plus or minus, because correlation have disappeared. It just become like from quantum randomness, and it just became classical randomness, and we're not able to see anymore about the quantum randomness to verify it or not, and yeah, that's why we destroy all quantum correlation. Um, and if we have changed the qubits plus and minus, we would have seen that the phase would have been totally annihilated, while in the we see like the phase has been totally annihilated. Well, here we will not have been able to see it with if you do not check about error. So to prove that we cannot destroy the quantum randomness, like we were, it's a must to have this error reference into the global system to be an entanglement witness in a way, like yeah, to see if we preserve the quantum correlation.